Good evening, everybody, and welcome to meeting number 7 of our Python data science study group. As always, I'm Michael Porter at Muddy Boots Code. Not a data scientist or not a data engineer or anything, just really like kind of messing with all this stuff like that. We have with us Nathan Smith, who's an actual data scientist at Lovevery, and as always provides excellent expertise and color commentary. And Jeremy McGraw, who we have yet to see, but we assume he's like an incredibly handsome individual who just doesn't want to steal the spotlight, from
that's exactly
the rest of us. And we appreciate him for that, because I for one need all the help I can get. in that deal there. So let me go ahead. We'll go ahead and share our screen here. We have finally made it to chapter two in our book. And so today we're going to be talking about data and sampling distributions. I think we've all probably heard at some point or dealt with the concept now at this point that I've seen the phrase "data is the new oil." These kinds of things where we now produce terabytes of data per day in so many different ways, and things that we search for, and things that we buy, places that we go, the way that like phone apps and things track what we do. We now create this massive amounts of data and data sets that are, I think, possibly we as human beings think that, okay, we've created enough data now that we can just figure anything out, right? We've got enough examples, we've got enough whatever else, we should be able to model anything at this point. And I think there's been enough failures and enough problems in our lives that we all know that that's not true. Like one day you're talking about golf clubs or something, and then Facebook is trying to sell you a golf excursion to Hawaii or something. These are the kind of things that we deal with now. But the very first line in this chapter is that this popular misconception holds that in this era of big data, that we don't have to sample, that we don't have to be selective in the kinds of data that we're working with, and then and pick out features and things that are meaningful. Like we could just search the entire set, or we can just use all of this and come up with good stuff. And I think what this chapter goes on to highlight is just exactly how important it is to predictive models and stuff, that your samples are correct, that they're well chosen, and that they're representative of the data that you're actually trying to find out. So, good Lord. We're not going to edit out all this coughing, folks. I'm sorry. It's a little bug going around the house. I've got a sick kid. He hasn't quite infected me to the point, but we're getting there. So what it goes on here to show is like I said, again, we're going to see a feature come up here shortly that shows the population of data, which is not analogous to like a population of like an island or a population of a nation necessarily. Like it's the population that fills up the data set. And then where it says traditional statistics focus very much on that entire population, most of our modern statistics methods and stuff like that, we've moved to the right hand side where we're sampling pieces of that population, and how we do that sampling and make that stuff work that's better. And like I said, one of the things here that it talks about, and maybe Nathan can kind of elaborate on it, is like I said, things that you don't have to sample necessarily, or some things like this. The data it's generated from like a physical process that could be modeled. In this particular instance, it's like the flip of a coin. right? We don't have to take samples of that process. We know that that's, this binomial distribution, this is going to be something that we can just go ahead and model, and we don't have to be like, oh, we only want the first 10 or the first 20 or whatever, something of that nature. Does that sound about right?
Yeah, in those cases where the answer can only be yes or no, then um, you can be certain that the answers are going to follow that binomial distribution. Often you don't know, you just have data points, you have examples, but you don't know if they're going to follow a particular distribution pattern. And so you have to figure that out, and you can make inferences and make judgments based on what the data looks like. But if you know that the process itself is very simple and straightforward, and it's just a yes or no question, like flipping a coin, then you don't have to think, oh, which kind of distribution should I use in this case? You know that you can count on it being a binomial distribution.
Mm-hmm. Okay. So that makes absolute sense. Like I said, yes or no is going to be this or that, and it's just a mechanical process. It's going to happen. We don't have to look necessarily at the same thing. But to go ahead and illustrate that example again of sampling data and doing whatever else you said. Here we have on the left, we have the population, which represents the entirety of our data set. And then on the right, we have a sample, which is just a piece of that data set. So it's just a subset of the later data set. And that statisticians call the big piece the population, and the smaller is our sample. So, so there are different ways to sample the data, same things that we're going to look at. The first one that we were going to talk about right now is this random sampling. And that's where just every single member of that population, every single data point in that population has an equal chance of being chosen. Okay. We don't go, hey, we only want to know which ones show up from 10 to 2. We don't say we don't want to, we only care about the ones that show up on Monday. That's not the kind of stuff that we're looking for. Everything can be selected at whatever point. And then that simple random sample, it can be done with replacement, which is where after it's been pulled out and we've got our sampling, it's placed back into our sample, or without replacement, where once we pull out our sample, that does not go back into that population. And so we remove those cases out. That way that observations once selected, they're unavailable for the future. So we look at that. Which, trying to think how to, I guess at some point that's going to like kind of stratify your samples a little bit or something. You're gonna, what's the exact logic behind like not replacing things that you've done? I said that you don't want to count them twice, maybe.
Correct. If you sample without replacement, then there's no chance of double counting anything.
Okay, makes sense.
So if you imagine a bag that's got black marbles and white marbles inside it, if you're sampling without replacement, then you're taking a marble out and there's one less marble inside there every time. If you're sampling with replacement, then you drop the marble back in, shake it up, and draw again.
Okay. And so one of those is going to give you, like I said, no double counts. The other may still give you the probability of pulling one or the other out, but it's probably maybe not quite so.
Yeah, I mean, if they were split half and half, then once you take that first marble out, the probability is no longer 50-50 on the next draw because you've already taken one out. So your calculations are a little different. Whereas if you would put it back in and then shake it up, then every time that you draw, you've got that same 50-50 probability of getting a black or a white.
And then there we are back in the whole binomial deal of all that kind of stuff like that. Mm-hmm. Okay, so the next little highlight thing probably shouldn't shock anyone or be difficult to deal with, but data quality often matters more than data quantity when making an estimate or a model based on samples. I think we've talked about before in our like interviews based on talking about what a data scientist does or what a data engineer does. And part of that is ensuring like the quality of data, running it through different processes and different things, pipelines, trying to make sure that the data that you get is very high quality. You're not missing features, you're not doing things of that nature. That's a major piece of when you start dealing with these problems is cleaning data and making sure that they're good. And then, like I said, data quality in data science involves completeness, consistency in format, cleanliness, accuracy of individual data points. And then in statistics, we also add the notion of representativeness, and which we'll get to here in just a second. But those key terms, again, sample, population, random sampling, a stratified sample, which is dividing the population into strata and randomly sampling each strata. Simple random sample, we talked about, we just pull from out there. We're going to get to bias and then sample bias. And one of the examples that this gives here is the classic example of the Literary Digest poll of 1936 that predicted a landslide victory for Alf Langdon over Franklin Roosevelt. And part of their problem is that Literary Digest, they polled a massive amount of people. It was 10 million people, and they predicted, okay, we asked 10 million people. 10 million people said Franklin Roosevelt, they're going to win. And then George Gallup, who's the founder of the now famous Gallup poll that you always hear about, he went out and he conducted biweekly polls of just 2,000 people, and he accurately predicted the Roosevelt victory. And it was all laid in the selection of those people polled. So one sample was representative of the actual population and the makeup of the nation, and the other sample, the Literary Digest sample, had really high bias because these were people who were all kind of like-minded. Now we hear all the time about, we were stuck in the echo chamber, right? Where, all of your Facebook friends think one way. And so all day long you get Facebook news of this or that nature. If you're an anti social media type person or whatever else, maybe you can escape it. But, now we get stuck with the labels, right? Like you're a Fox News person, or you're a CNN person, or an MSNBC person, however that plays out for you. But the Literary Digest, like I said, again, they paid zero attention to who they selected. They were like, oh, you buy our newspaper, we want your opinion. And what that turned out to be was not a representative sample of the nation, and they incorrectly predicted the election, which I think has resulted in the famous newspaper, famous picture of, oh wait, hold on, that wasn't Roosevelt, that was Herbert Hoover.
Truman.
Hoover.
Dewey defeats Truman.
Yeah, that was it. And I don't know if that was from the same type of error, the same type of problems, but it's kind of interesting to think that maybe it might have been, resulted in that kind of stuff like that. So, like I said, the result was sample bias, and that's just to say that it was not their selection out of the population of people that they polled. It wasn't meaningful, it wasn't non-random, and it didn't represent the nation as a whole. And so that term non-random is important. It says hardly any sample, including random samples, will be like exactly representative of the population. The stuff that we do, how we look at information, how we ask questions, the things that we do, all have bias, and they all have things that you have to work hard against. But that's kind of like your job as someone who deals with data and someone who wants to ask questions and find out things, is that how do you get a representative sample? How do you narrow down that population into the sample that you're looking for. So I guess it's that the why questions are super important, and then we start figuring out how to get there as we cut away at our population and pull our samples out. One of this little deal talks about self-selection bias, and it's kind of a neat blurb because it's about people who write like Yelp reviews. So if you're the type of person or know the type of person who you go to a restaurant and you sit down and you start writing a Yelp review, because it makes you feel like you have like power or like an ability or something to, to influence other people, or perhaps you are an influencer, you're a restaurant critic or something of this kind of nature, you're introducing your own kind of bias into what's going on there, because your experience is probably either it's not going to be representative of the experience of the majority of the people that go to that restaurant, possibly.
Yeah, I hate it when I get those. People will offer you a gift card for writing a positive review. Or when I used to take my car to the dealership, I would get an email saying, you're going to be getting a survey from the manufacturer, and would you please give us 5 stars? If you don't feel like it's 5 stars, then call us up and talk to us about it before you fill out the survey. And so they're purposely biasing the data. It makes, I mean, not that I think it's worth a pen of my time to fill out their surveys anyway, but knowing that they were deliberately attempting to bias the survey really kind of made me mad. So I never responded positively when they sent me those emails.
Oh, I was going to say, they didn't know who they were dealing with.
Exactly.
They had no idea
yeah, they need to do a better sampling of who they asked to do that.
Exactly. Yes.
So they're like, hold on, what do you do for a living, sir? It's just going to go against your moral code in life to write a positive review.
That's right.
No matter how you feel about this. And so that kind of stuff, I said, it's neat to me, but absolutely like that, that's a great story right there. It's like, you don't know who you're talking to here. Write your review. So that first thing that we pop up into here, of course, again, as I said, is what we talked about as bias. And that bias refers to measurement or sampling errors that are systematic and produced by the measurement or sampling process. And so, the bias, you have to watch out for your bias, and then if you do have bias, you have to recognize that bias is in the data and then what you're doing. One of the things that it talks about here is that, if if you're shooting a gun, and let's say all things considered equal, unless you're an expert and you have a very controlled set of circumstances and whatever, that your shot pattern is probably going to fall. There's, there'll be a center and they'll fall out. And as somebody who used to teach a lot of firearms instruction and doing a lot of stuff like that, when you zero a rifle, you don't take one shot and work from that. You take a group of shots, you find the center of that group of shots, and then you move, you adjust your sight, you adjust your scope, or however, based on the center of that grouping and not just the one shot, because you want to know what your true, actual point of aim is and point of impact. And so, here's what it's showing is in our first scatter plot here, you've got a weapon that it's got true aim because, all of your shots are kind of equally distributed around the center of that scatter plot. And then as a weapon that's either does not function well, or the sights are not tuned in correctly, or whatever else, you have the second scatter plot where almost all of your rounds are impacting over there on the right side of the target, showing that something is not right. There's bias in what we're doing, in whichever way that's playing out. Either the firearm is malfunctioning, or you you don't have the sites dialed in right, something of that nature. What's going on there? So the bias, it comes in different forms. It can be observable, it can be invisible, and when your results do suggest bias, when you're referencing stuff like that, it's something that, like I said, you need to check out and make sure, like I said, that you're misspecified, or you've left some kind of variable out, or you've made some kind of misassumption about what you're doing and what you're looking at. So random selection is, so what happened, they go back to the example of the Literary Digest predicting Roosevelt losing, as it is their data was not a random sample. They selected a biased sample because they picked their readers, and they picked people from only certain places and certain socioeconomic circles and stuff. And so it wasn't really scientific. It was a large data set. It was much larger than Gallup's data set, but it was not correctly sampled, and it was not, the biases and stuff weren't checked for. And so, like I said, now that we look at this stuff, I said the heart of most of these the data sampling methods is this idea of random sampling, and making sure that sampling is representative of what we're going to do here. So proper definition of an accessible population is key. And so again, here it goes into, you want to generate profiles of customers. You want to go ahead and do something, you need to start asking questions. Well, okay, what kind of customers are we after? Are we after our average customer? Are we after the customer that spends less than X amount of dollars? Are we after the whales? Are we only after the top 10% of our customer base? Are these the kinds of, and at that point you can go ahead and start choosing your samples and working on that kind of stuff there. I was going to say, at I'm not sure where your stuff falls in at Lovevery, but maybe that's something that like you can speak to as far as what kind of samples you choose to work with there.
Well, we do have to be careful, and I think time is an important factor as well. When I talk about, do we include all past customers, because customer behavior has changed a lot during COVID, and now hopefully we're moving into a post-COVID period. And so the sample that you take from 2019, the behaviors that you observe there might not be relevant anymore. And so that's an important thing when we consider who's a representative sample of who I'm interested in, who's going to be making a decision to subscribe today versus who was subscribing some time ago.
Yeah, I was going to say, I hadn't honestly even kind of thought about that, how that would be, how you would affect something like, I mean, for a company like Amazon, where COVID was an absolute like godsend, right? Mm-hmm. They exploded and drove them through the stratosphere, because now all of a sudden, they can deliver packages without delivery people, and then they need 1 billion people to work in warehouses and fulfill customer service roles, because all of a sudden no one's going anywhere and everyone's having things delivered in a scale that they couldn't imagine beforehand. And for a company like yours, which delivers toys and things of that nature, for a specific age group of stuff, you probably had, I don't know, like an explosion in people who were now home and learning at home and stuck at home, and now had an entirely new kind of not customer base, but customer activities and customer interactions to look from. And so that would be a really interesting, I'm sure those are really interesting conversations.
Yeah, definitely.
Around the water cooler there. So as we move through that, when we sample and we decide what we're going to look at, the next concept that we have is a stratified sampling, that this population is divided into strata, and random samples are taken from each of these stratas. And so, like, these political pollsters, they're gonna they're going to go ahead and go, okay, look, the population of the US is, this percent Caucasian, this percent Hispanic, this percent Asian, and to be sure that they're representative and to be sure that they're sampling correctly from the entire population, they're going to have to stratify. And that's what SpaceX does. They stratify stuff.
There's the stratosphere, yeah, which is the upper layer of the atmosphere. But here we're talking about stratifying and strata. That's right.
Get proper stratification in your data sampling and make sure that we're getting the kinds of things that are going to lead you to a representative sample of the population when you're doing this kind of stuff like that. And so, again, we're going to have this question as like size versus quantity. When does size matter? And it depends on the question is the answer, right? We do have access to such massive data sets, but in those, you're probably going to be in most questions, in most scenarios, you're going to be better served with a smaller, more quality data set and sample out of that than you are going to do like these massive data sets and stuff like that. So in addition to some of these massive data sets being like computationally expensive to deal with or hard to get around in, the quality in the data of them may not be that great. You may be missing a lot. There may be a lot of null values. There may be a lot of things that you're not looking for and stuff like that. So that manual process of collating that huge, massive data set is probably going to hurt you a little bit when it comes time just looking for that kind of stuff. And so, it says, when is massive data needed? And, the classic example is when the data is like very sparse. For Google, where basically you're doing search terms and so the enormous quantities of data that are accumulated, effectively the search results can be returned for most queries. And so, and things like Google, where you want to know how many links we have back, and their graph model back to that page that has the most links that goes out of it, most relationships out of it. That's a great place to have massive amounts of data. And you trying to figure out, like you said, your best customers and ways to reach out more people. It's probably not as desirable to know like what every parent in America buys their child or something of that nature.
Yeah, another example where more does seem to be better is in machine translation or natural language processing in general. Those are trained on huge corpuses, very expensive to train some of those big models, but they have generally found that showing the model more examples usually helps. Also, I think in computer vision, that's why all the reCAPTCHAs are having you pick out the pictures, because they're training computer vision models that way. So for some of the things where it's very sparse and the level of complexity behind the model is really intense, when we're approaching that human level type of AI, then often more data is better. But when we're using more traditional approaches, I agree with the author here that a good quality sample is better. Always a good quality sample, a good quality smaller data set is going to be better than a biased big data set or a junky, dirty big data set. But the other thought behind this is that if the errors truly are random in that big data set, then they should cancel each other out. And so having a whole bunch of thermometers that are only marginally accurate is probably better than putting all your money on one thermometer that you hope is perfectly right. Mm-hmm. And so there can be situations like that as well, as long as the inaccurate thermometers are equally likely to be off in different directions.
Got you. Yeah, that's that. Actually, I've looked. I forget what it was. There was one of the things that I just recently read, and it was basically talking about taking a lot of like smaller quality, really good data sets, and then basically using those to aggregate larger data sets, but make it was basically virtual data. Like they were sampling it out, and then instead of and actually collecting data and actually doing whatever else, they were modeling it off of kind of fabricated data sets, but data sets of quality. And it was an interesting. I can't for the life of me remember what the term was exactly what they were doing, but
Yeah.
it's not virtual data sets because that's not correct, but it was something along it.
One of the challenges with big data is getting it labeled. So, you've got a whole bunch of radiology X-ray pictures, but you have to know this one's cancer, this one's not, and you've got to have them labeled appropriately, and then you can train your machine learning if you don't have it labeled. And so there's kind of this whole process sometimes of semi-supervised learning where you can give them a small, highly accurately labeled set of data and then use that to infer labels for other ones that weren't hand labeled by experts, because that labeling process is very time consuming and expensive for many kinds of machine learning problems.
Mm-hmm.
So that's another example of kind of sampling, but then using that sample to grow a bigger data set.
I think Jeremy, didn't you have at some point a project where you were given like samples of like EKGs or?
Yeah, this was more just for, but this was allowed to allow doctors to classify them. So they had like a number of, so generally a doctor will look at like 10 seconds of an EKG and just kind of make a determination off of it. So my brother wanted a way so they could kind of compare, well, here's what, a doctor's 10-second intuition said, and here's how then like they ultimately classified it, or how a machine would classify it. So to kind of investigate how the doctor would classify it versus the accuracy of a machine looking for certain spikes as it pertained to, I think it was seizures he was studying. But they never actually ended up using it. It kind of got put on hold, but I built it. So
nice.
Oh, but that's the point. That's the point,
Yeah.
though. Is you build that, and then when you talk about the expense, is you have a doctor whose time is worth X number of dollars an hour sitting there classifying these EKGs, or these, or a radiologist or a trained sonographer or whatever, somebody who's looking at this stuff and is spending their time labeling, and like you said, and then they've got to make these determinations and create these data sets.
Yeah.
So that I remember that being a cool example of something that we can do there. So this goes on to talk about basically how Google breaks down searches, like natural language searches and things of that nature. At first, in the first days, like the search results were not that great, and it took a long time. And then, finally now, the graph is, now that we're into it, now we're, trillions of search queries have been accumulated, and all of those relationships have been mapped and all that kind of stuff like that. And so now it returns much more pertinent answers. Like the results that come first are better. I think what's the joke? It's like it's been seen less times than the second page of Google results. Google search page or whatever.
Yeah.
So that kind of stuff keeps going on, and I said as always, I love to throw Neo4j stuff out here and play, but I love like the Google, the graph model for what they do for their searches and how that works. It's just interesting stuff. So again, the actual like pertinent information in these massive data sets is what's important. And then, it took so much data to get there. It took trillions of search results to finally kind of like sift the wheat from the chaff, as it were.
Yeah, I'm always impressed with how there will often be something like really archaic I'll be searching for, but it'll like, so there's this one song I happen to like by, I think, the Seventh Element or something like that, or I think Vitas is the name of the band. But like, I always remember it because he does this weird thing with his tongue when he sings. So if you do a search for like weird tongue singer, it pops up as like the first search result, and it's just like, no, all right. I guess a lot of other people influenced that search result by all, like, they couldn't remember the song. They're just like, I don't know, it's just some weird Russian guy with it doing something with his tongue, and then there you go. It's always the first search result.
That's great.
Oh. Well, and that, it shows how alike people are, right? We have the autocomplete, stuff like that. You're like, it's that weird guy does the tongue thing, and you see how many people have actually have searched for the same thing, and then the results that come from that, as that kind of stuff. Have you seen any of the Wired autocomplete interviews?
I don't think so.
They're kind of fun because what they do is they'll put like a celebrity, in front of the camera, and they have these little boards, and they're like what autocomplete pops up when they do stuff. So it's like,
Oh yeah.
it's like, does Morgan Freeman, and then he like peels like a label off, and it's like,
Okay, yes.
does Morgan Freeman, actually speak with God's voice? And then like they answer questions and stuff. They're fun. I like that. Maybe we need to do like a data science Google autocomplete interview or something. That'd be fun.
Yeah, what's the public's perception of this person versus what's the image they want to present?
Absolutely, that stuff is fun. So we're getting here. So this is our when we get in here, we're continuing on with our sampling stuff here. So sampling mean versus population mean. This symbol, whatever pronounced X bar, is used to represent the mean of a sample from a population, whereas, and all my math is rusty. What?
That's a mu. Yeah, I mean, it was nice of them to tell us how to pronounce X bar. They could have told us how to pronounce the Greek letters.
right. We got X bar, but mu. Yeah, you're on your own, guys. Yeah, you either A, better be Greek, or B, your math better be up to speed there.
Yeah.
I think.
Or C, you use microtorrent.
Yeah, there you go. Absolutely. What did you say you actually, like, you were using? You had to go back and use like trigonometry at work or something.
I did. Yeah.
So that's some stuff you have to dig off in there. So
Exactly.
it's used to represent the mean of a population. So why make the distinction? What's the mean of a sample versus the mean of the population? So that's important, right? The mean of the population could be entirely different, from the mean of the sample that we're observing. And information about large populations is often inferred from smaller samples. And so statisticians like to keep those two things separate in symbology, which makes sense. It's important. But I guess maybe that just, in me, I would just be like, I would just say, okay, well, here's the population mean and here's the sample mean. But yeah, I'm a Marine and I used to eat crayons, so who knows? So we are at the end of chapter 2, data and sampling distributions, and talking about the things that are important. Why we need to do samples and what kind of populations we do. Why bias is important, why random selection is important. Why size versus quality is important, and what those two things are good for and bad for. And then here we are again making the distinction between the sample mean and the population mean. So again, things to take away from today, besides that Jeremy is, devastatingly handsome and will never show his face. Is the key idea is that, even in the era of big data, that random sampling remains like super important. That helps you get to the core of what you're really actually trying to find, even though you have these large, massive data sets. Bias occurs when those measurements or observations are systematically in error, because they're not representative of the full population of your data. And then data quality is just often so much more important than data quantity. And if we make sure that we correctly sample things, then we can reduce our bias and, facilitate the quality of our data and the things that we use. So these are, I think this is just kind of leading into just how important it is to make sure that when we ask ourselves a question that we want to have a model for, or we want to have an answer for, that we take into account exactly what population we're doing and exactly how we're going to sample that population to make sure that we have the most representative information with the least amount of bias, which we should all, I think, aspire to, if we can work that out. But let's see if there's anything else here. Further reading. So a useful review of this stuff can be found in Sampling Methods for Online Surveys, the SAGE Handbooks of Online Research Methods, and then the story of the Literary Digest poll can be found at the Capital Century website. It's probably interesting reading. Gets a little further into that. But I think that brings us to the end of Chapter 2, Section 1, Random Sampling and Sample Bias. I don't know if we have